Hello everyone, my name is Rosemary Alden. I'm a USP student with the Spark Laboratory here at UK. Today my presentation is on AI-based electric load forecasts for experimental smart homes, including HVAC, electric water heater, and PV component predictions. Within this presentation, I will explain my research into electric load forecasting using deep learning, long short-term memory models. I will start by introducing my data source, the Shines Homes, and the details of the model in use. I will then present example predictions, error analysis, and its use with the home energy management system. I used a single dataset, the Shines demonstration homes in Pensacola, Florida, and predicted the total HVAC, solar, and water heater hourly average power during the daylight hours from 6 a.m. to 9 p.m. This was predicted using the summer months only, based on 3 years of data from 2018 to 2020. The Shines dataset includes 2 homes, and the differences shown in the rightmost column can be attributed to the influence of human behavior. Significant differences can be seen in the HVAC and total generation heat maps. The machine learning model uses the encoder-decoder variation of the long short-term memory model, which is a recurrent neural network that was selected for its ability to learn long-lasting patterns. The weather inputs for each prediction variable are shown in the chart on the right. The model receives the previous 3 days of hourly power usage, 2 previous days of weather data, and 1 future day of weather data as a perfect forecast. It predicts the next day's power usage for each hour from 6 a.m. to 9 p.m. The quote-unquote perfect forecast allows for the influence between the weather variables and the power usage to be captured to showcase a high standard for how well the long short-term memory machine learning models can predict residential power usage. Initial developments of this model were published in the Proceedings of ICRERA 2020. An example week from July 31st to August 6, 2020 is shown for each prediction variable: HVAC, PV, the total, and water heater for both House 1 and House 2. This week shows the model following the trends of the actual power usage for the HVAC in House 1, right here, as well as the PV, better than in House 2. Total and water heater are similar for both houses, with the water heater being the hardest to predict. Water usage is entirely dependent on human behavior, and the total has the influence as well, indicating that the variability of human patterns is the most difficult thing to account for in data-driven machine learning electric load forecasting. The RMSE for each prediction variable was calculated and is shown on this slide. Upon investigation, the RMSE values seem high in comparison to the max power used, the approximate range for each device. To see farther how the model predicted, the distribution of residual error is shown for each component in each house, with House 1 being the top row and House 2 the bottom. The HVAC and solar cluster around 0, with the most frequent error being near 0. The distributions show that the majority of the hours the LSTM model performed satisfactorily. The House 2 HVAC was more irregular than House 1, and that is reflected with a more spread out error distribution. It is important to note that the water heater appears to be the best prediction, but is actually the worst from comparing the results visually. Electric load forecasts are useful to home energy management systems, as load shifting and demand response schemes can be implemented based on the predictions. This pairing of data-driven machine learning electric load forecasts with the smart home energy management system is under development, and initial progress for my group is under review for publication in the digest paper shown on this slide. My ongoing work is further development to the LSTM encoder-decoder model. Comparisons of different machine learning models, such as support vector regression, multiple regression, and neural networks, as well as comparison of the performance between residential homes with a more detailed error analysis, including daily energy error. This graph shown on this slide shows initial results for a comparison to different types of models, as well as the daily error comparison. Finally, the application of the electric load forecast to home energy management system will be continued. A special thanks to my research advisor, Dr. Dan M. Iannell, my NSF co-advisor, Dr. Chris Ababe, and graduate PhD candidate mentor Wanji Gon. Acknowledgements and thanks to the Science Foundation for its support of my research as well.